Hello, guys and ladies, of course. Um, Here we have Introduction to Statistics, Part 2. And I know it took a while for me to upload the second part to this. I've been extremely busy. I just started my PGY2 in oncology, and this is the first year they had this program in the institution. So, I had to like really dedicate a lot of time into structuring the whole residency basically. But anyways, let's get back to this. So the topics for today, as you can see here, you could like read it on your own. I'm not gonna go through each one, but we will of course go through each one. Ironically. Um, but yeah, the goal of this is to explain it in the best way possible for you to understand. So if I'm unable to do that, just make sure you ask me these ask me these questions, okay? Like comments or anything like that. All right, let's move on. So to begin with, sample versus population. Okay, so sample, right? So let's start with the question first of all. Let's just go through it. What's the average height of dogs in the United States of America? The only way you will know this answer is if you go around and you measure every single dog in the United States and write the number down. Okay, after that, we will add all of them up and divide by the number of dogs you measure, right? And then you will get the average. But, like, think about that Instagram meme of that lady. Who got time for that, right? I should have posted a picture of that. Yeah, right. Nobody got time for that. So what they normally do in real life, or like I should say, in clinical practice or research, is they take a sample, right? Now a sample is just selecting a portion of that population that you wanted to, like the taking a sample of the population that you actually wanted to do the research on. That's literally what that is. Okay, so it doesn't matter what the population is. Let's say you wanted to know um, what is the most common favorite color of everybody in the United States, right? It's impossible, right? So you take a sample of that to do that. So here we select only 500 random dogs from the United States and take the average, and that will be your sample. Pretty straightforward, right? So next question, same question actually. So here we will, like I said, assume that after sampling the 500 dogs, we found that the average is 40 centimeters, and this is an arbitrary number. Okay. Now the follow-up question is, how do you know that it's 40 centimeters? How are you so sure that that's like the true average or the true mean of dogs, right, in the United States when you only sampled 500 dogs? You didn't even sample all the dogs. You only sampled 500, and now you're gonna come here and tell us that 40 centimeters is the true mean. Hmm. That's when confidence interval and confidence levels come in. Okay. Now, confidence intervals are usually presented as a range. Okay, as we will see later on, I'm gonna have an example showing this. Now, it is highly possible that 40 centimeters is actually not the true average of height, right, of all dogs in the United States, which makes sense. Why? Because we sampled 500 dogs, right? Trying to use this number to compare to the whole population, so it's possible. It's possible that we may not be accurate. But with confidence intervals, you get to have a range, right? So you get to say basically, um, for 40 centimeters may not be the average, right? Let's just say, but I have this range, let's say 20 to 60, and I'm pretty sure that the average or the true mean falls in this range, okay? And then, like I said, the true mean in this case would be the average height of all dogs in the United States. Now, confidence intervals can be calculated, right? It has a very complicated formula. So I honestly don't know it. I mean, I looked it up, but I didn't feel like I needed to include it because they usually give it to you on exams. Now, the confidence interval for exam could be 30 to 50. With that, we could say that we are confident that the average height of all dogs in America is between 30 to 50. Now, a follow up question after that will probably be okay, so how confident are you, right? That the true mean of the average height, right? The true value of the average height of all dogs in the United States is between 30 to 50. And that's when confidence levels come in, okay? So with confidence levels, you're basically replying to that follow-up question, right? So I'm 95% confident or 99% confident that the true mean falls between this value. So really, it's just a level of certainty, uh, of this conclusion that you came with. All right, and this is also usually provided on the exam, man. In clinical practice, we usually use 95% confidence um, intervals. Okay, so you can some people do 99%, which so everything is calculated based on that, right? So your confidence intervals will be calculated based on your level of confidence, right? So give me a so let's say if you like the lower your level of confidence, right? Right? That means the range is probably bigger, right? So you're unsure that the true mean will fall in that range. Then we have standard deviation. Right? Now with standard deviation, we want to measure when we measured all 500 dogs, we had different centimeters for each dog, right? So one dog could have been 20 centimeters, another dog could have been 30 centimeters, another dog could have been 100 centimeters, whatever the case is. We had different numbers. We had different numbers, right? The highest number and we have the lowest number, and we have a bunch of numbers falling in between. Now let's assume that 40 centimeters is the true mean, the average, right? The middle number, right? That means any measurement close to the mean is good and accurate, correct? So in that case, you would say that somebody has a low standard deviation, okay? So because standard deviation simply means how much variation or dispersion is there from the mean, okay? How far are you from the mean of 40 centimeters? Like I said, the closer the mean is to the mean, the closer the data is to the mean, the smaller the standard deviation. Okay, and this is usually provided to you on exams. It has a complicated formula also in order to calculate it. So they usually provide this on the exam. So this is a picture of showing like what a bell curve is, right? It's good distribution from left to right, right? It's like symmetrical. You can split it right in half, right? So this is what you call like a bell curve, okay? Now here, based on the standard deviation that you calculate, right? You could go, let's say, one standard deviation away from the mean, right? Or two standard deviations away from the mean. This is the mean, by the way, sorry, not the standard deviation, this is the mean, okay? And as you can see, as the standard deviation increases, you're going further away from the mean in the middle. Next, we have p-values. Now, p-values allow us to make quick decisions about whether something is statistically significant. And I will talk about exactly what it means when something is statistically significant later on. But p-values are usually less than 0.05. And I will go into a little bit as to what that number means, okay, as we go on. But usually it has to be less than that. Um, it's basically saying that there's a less than 5% chance that my conclusion, right, is incorrect, basically. and it reflects the strength of evidence against the null hypothesis. Now, what is the null hypothesis? The null hypothesis is basically is what the researchers are trying to reject, right? So it could be like a statement or a fact. So the null hypothesis could say the world is flat. The alternate hypothesis, or the hypothesis that researchers are trying to show that is true, right, is the alternate hypothesis. Sorry. So that would be the world is not flat. So keep in mind these two things are always opposites, right? Your regular hypothesis, which sometimes referred to as alternate hypothesis. Then you have your null hypothesis. All right. So they're always opposite with a p-value of 0.04. So since this p-value is less than 0.05, right? Because we're basically saying there's a less than 5% chance, or in this case, there's a 4% chance that our alternate hypothesis is not true. Okay. In the previous example, the p-value is what determined the significance of the alternate hypotheses, like I mentioned. Since it's less than 0.05, which is also 5%, it means that alternate hypotheses is true. Why? It's because we given ourselves a less than 5% chance of making a mistake, and in this case, we achieved that. We achieved it with 4%. But there's only a 4% chance that actually the world is not flat. Okay. Um, so since our alternate hypothesis is true, we are rejecting the null hypothesis. The null hypothesis was the world is flat. So I'm rejecting it. I'm saying no, the world is not flat. Why? Because my p-value said so. Now, if the p-value was greater than 0.05 or 5%, then we have to reject the alternate hypotheses and accept the null hypothesis. Okay? Now remember, p-values are usually set in the beginning of studies. Like, okay, the results should have a p-value of this to be significant. And that depends on many things, right? Like certain risks. Okay, which I will talk about as we go on. Most likely next, I believe. Now there's errors occurs when rejecting or accepting the null hypotheses. Like we think we're rejecting it, even though the p-value is significant, we think we are doing the right thing, but there's still a 4% chance, right? Or 5% chance in this case. And with that little chance, sometimes we fall into that. Where we will say that this is what it is, but in reality it's not. And that brings me to type 1 and type 2 errors. Now, type 1 error is when the null hypothesis is true, but instead we rejected it. So the world is actually flat, but instead we said it's not flat. Now our p-value told us that the world is not flat, right? Because it was less than 0.05. And that's what made us accept that, yeah, okay, so the world is not flat. But then there was that small chance, right? That 5% chance of the world actually being flat, even though your p-value is less than 0.05. Okay? So that's basically what they're trying to say for for the type 1 error. So here we go. We concluded that there was a difference between the two groups, but actually there was no difference. Type 2 error. When the null hypothesis is false, but it is accepted, right? So when we reject the alternate hypotheses, right? So let's say the p-value was actually not less than 0.05 in this case, right? But when we did the study, the results showed that the p-value was, let's say, 0.09, right? So we said, okay, this is not significant, so that means what we did was wrong. So we rejected our hypotheses and accepted the opposite of our hypotheses, which is the null hypotheses. Okay? But in type 2 error, you accepted the null hypotheses, but in reality, it is wrong. You weren't supposed to accept it. Even though the p-value was greater than 5%, right? The results. Um still, still, you accepted the wrong thing basically. That's a type 2 error. We concluded that there was no difference between the two groups, but actually there was a difference. Clinical significance versus statistical significance. And it's very important that you distinguish between these two things because you're going to come across this all the time. Now, clinical significance reflects the clinical value of the outcome. Okay? So how valuable is it? Like your results show this, but how is it going to impact clinical practice? And if it causes a huge impact, that's or if it causes a significant impact, we could say that it has clinical significance, right? Or we could say that the results are clinically significant. For example, a new drug shows mortality benefits. Most likely, this medication is clinically significant, right? For example, in oncology patients, like if it showed that it helped patients live 5 years longer, that's clinically significant right there. Or a new drug that decreases blood pressure by a higher value than other drugs on the market. That's clinically significant. It made an impact, right? It reduced. Let's say if most drugs on the market that reduces blood pressure only reduces by 10, this new drug reduces it by 20. Most likely, it's going to be first line now, right? That's a clinically significant outcome. Sorry. Then we have statistical significance, and this reflects the strength and accuracy of the data. All right. So we are referring to the data in this case. How strong is it? So a new drug may show in research to reduce blood pressure by 3, but it doesn't decrease mortality. Oh, by the way, so it reduces blood pressure by 3 with a p-value of less than 0.05. I should have put not. Yeah, not that's a mistake. Okay, so it's less than 0.05, not 0.5, guys. Um. So yeah, so it reduces your blood pressure by 3. Okay, p-value just told me that this is true. This is statistically significant, but it's not clinically significant. Why? Because, for example, it didn't decrease mortality, or it didn't reduce the blood pressure greater than any other agents on the market. It actually did worse. So yeah, your p-value told me that your result, right, is most likely true, but it didn't really, impact our clinical practice. We're most likely not going to use this medication. And that's the perfect examples of clinical significance and statistical significance. Next, alpha versus beta versus power. Alpha is the same as type 1 error or p-value, right? So your alpha must be less than 0.05, which is 5%, right? Now this means that we are allowing only a 5% chance of a type 1 error to occur in the study. Don't get confused. Let's look at the next bullet. You're going to understand this. If a study concludes that a drug is safe when it's in reality it's not. Now guess what? How did they conclude that the drug was safe? Well, they looked at the p-value, right? And remember what a type 1 error is, right? When a p-value tells you, okay, accept the hypotheses, your hypotheses. We accept that this drug is safe in people, right? But in reality, it's not. So wait, we concluded that this drug is safe because the p-value looked good. But you're telling me in reality it's not. Well, that's a problem. Because once we accepted that this drug was safe to be given, most likely we're going to start giving to patients, right? and then we find out that it's actually not safe, in this case, it may cause harm because patients took that. So that's why we only allow a 5% chance of this occurring. You get what I'm? Do you like get what I'm trying to say? Okay, because with with alpha and with alpha, right? The reason why it's so low is that it could lead to harm. That's why we only give it that percent of a chance of occurring in studies. Okay, so that's why it's usually less than 5%. And you're going to see with beta is the same concept, but it's usually less than 20%. And in this case, we are referring to a type 2 error. When you say no to my hypotheses, right? No, this drug is not safe. Wait, in reality, this drug is safe, right? So that's when you commit a type 2 error, right? But in this case, once you said, no, this drug is not safe, we won't give it to anybody. So no harm is involved. Even though in reality it is safe, you concluded that it's not safe, so we didn't give it to patients, so there was no harm or risk involved with that. And that is why a type 2 error, in this case, or a beta, allows you to, it gives you a 20% chance of that occurring. Okay? Wait, power. Let me talk about power. I think I included it in here. Um, Okay, now the power right here. So power is like actually is closely beta is close. Power and beta are closely related, right? Power is simply one minus beta. So like I said, beta is usually less 20% or less. Uh, so your beta could be 20, right? In this case, it'd be 1 minus 20. Your power would be 80, right? Well, the one means 100, right? 100, of course. Or you could put this in decimal, then just subtract, right? And you're gonna get 80. Okay, so that would be your power. Um, so the power is usually 80% or more. So they usually calculate that in the beginning of a study based on a sample size. Okay, so they usually will say something like, we need a sample size of, let's say, 20 in each group, right? There's two groups they comparing. 20 in each group in order to reach a power of, like, let's say 90%. Okay. So that means with that, you're so the power, the higher the power, the more confident, right? The more confident or the more likely you are to find a difference, right? To find a difference, a true difference in a study when you compare them, right? So because as your power increases, the chances of a type 2 error decreases, right? So the chances of you saying no, my hypothesis is not true when reality it is true is decreased, right? You decrease that, and with that you get to like increase the chance of actually finding the true difference, right? The truth from the comparison in the study. And that will bring me to the end of this video. I hope I explained it in a way for you guys to understand. I'm sorry if you heard like this fan, this noise in the background. That was my fan, but I hope you could adjust the volume so that you could hear what I was explaining and teaching. So I'm gonna make the next part to this. I'm going to start working on that. So just be on the lookout for it. I believe the next one I will talk more about, let's say, relative risk reduction, absolute risk reduction, hazard ratios, odd ratios, um, those kind of things. Okay, so I don't think you want to miss that because that's something that a lot of students, especially me, back when I was in school, I used to struggle with. But it's pretty straightforward, and you can count on me to break it down for you to understand. Okay. So with this, I will end this video, and I'll see you next time.